So yeah, so far we've talked about two ways to solve systems. Graphing was one of them, and substitution was the other. All right, those are the two methods that we use to solve these systems. Today we're going to look at a third method, and the final method, at least the final method we'll learn. There are other methods. One of the things we looked at right before the break is I showed you how to solve this in the calculator if you've got the equations in y equals form. And we can go back and review that if you'd like, maybe on our review day. But this new method is called elimination. And in some cases it's easier than substitution. And in some cases it's a little bit more challenging. So here's how it works. The very first thing that needs to be set up here in order for elimination to work out is your equations have to be in standard form. Okay, in other words, they've got to be in that ax plus by equals c format. Not only that, but you want the like terms to be lined up. So you want your x's to be sort of vertically aligned, you want your y's to be vertically aligned, and you want your constants vertically aligned. So let's just dive into one of these, and I'll just show you how it works, okay, and show you some of the nuances that can sort of pop up on some of the more complicated ones. This is supposed to be a 3x, by the way. There's a little 3 there, got punched out. Okay, so notice that right away, both of these equations are in standard form. Yeah. And so we can do this method called elimination. Here's how it works. Basically, what you want to happen is you want to combine the two equations in a way that's a little different than the substitution method. So with the substitution method, the way that we combined the equations was isolating one of the variables and then sort of substituting it into the other one. In this case, what we want to do is combine the two equations by either adding them together or subtracting them in a way that one of the variables is eliminated. So for example, if I were to combine these two equations by just adding them together, like vertically, like if I write plus, and I just add the columns going straight down, what's 3x plus 3x? 6x. And then what's 2y plus negative 2y? Like 0y, so 0, nothing, right? And so what happens here is that the y's are effectively eliminated from the equation. Okay, that's what you want to happen, and that's why this method is called elimination. What's 4 plus negative 4? 0. So we get this equation that's just a one-step equation from here on out. Divide both sides by 6, although you probably can see what the answer is going to be. We get x equals 0. Now once you get the first variable, you kind of have to go back to the old substitution method. You can't really get away from that entirely. But if you use this elimination method, getting that first variable is a lot easier if it's set up this way. I mean, look, it's just like one step, boom, done. So to get the second variable, you're going to do the same thing that you would do in substitution, which is you just go back and plug it into one of the equations and solve. And most of the time, it doesn't really matter which one you plug it into. So like if I plug it into the first one, I get 3 times 0 plus 2y equals 4. 3 times 0 is 0, so this whole thing is just 0. And so we get 2y equals 4. Divide both sides by 2, and I get y equals 2. So we've got our x and we've got our y, and that's all you need for your solution, right? What we're trying to find is that coordinate, or that xy pair, that satisfies both equations, and that's it. It's 0, 2. So my solution is that coordinate. So that's how elimination works. Now there's a couple little tricks to it, like for instance your equations might not be set up as nicely, and I'll show you how to kind of get around that. But that's the basic idea, okay? So to do elimination, you want to make sure that your variables are aligned, like your x's and y's, and then you want to try to combine the two equations, either by adding them together or subtracting them, whichever way will eliminate one of the variables. You get your first variable, plug it back in, you get your second variable. That's the overall strategy we're doing. So we're going to just do a bunch of examples with that. So let's take a look at the second one. Now, if I add these two together, let's just take a look at these real quick, just sort of scan it. Which variable does it look like is going to be eliminated? The x or the y? Yeah, the y. If I add these two equations together, I get 5x plus 1x, which is 6x. 6y plus negative 6y is just 0, so that goes away. And then 50 plus negative 26 would be, what, 24? And then once you get that set up, the first variable should be very easy to find, right? You just one-step equation. We divide both sides by 6, and I get x equals 4. All right, so we get x equals 4, right? So what do we do with that? How are we going to find y? Yeah, just plug it back into one of the two equations. And it, most of the time, doesn't really matter. You try to pick one that looks like it might be a little easier to solve. You know, to me, like the second equation looks like it's got less stuff going on. It also has more negatives, so it's kind of, you know, it doesn't really make a big difference. You just pick one and go with it. So I've got 4 minus 6y equals negative 26. And so now I've got this two-step equation. This is the type of equation we solved in the very first unit. So we need to subtract 4 from both sides. Thank you. And I get negative 6y equals negative 30. So what's y going to be? Divided by 6. 5. Yeah. Okay. So y is 5. We've got our x. We've got our y. And so my solution is going to be 4, 5. All right, let's take a look at a few more. And these are going to be a little different. All right, take a look at this one. If I add those two equations together, which variable will be eliminated? Yeah, neither one, right? If I sort of add these together, I get negative 15x. If I add these together, I get negative 3y. So neither one of them get eliminated. And so you're not going to be able to solve it like that. So what we need is a little bit of a workaround. Okay, and this is how you're going to do that. One of the things you're allowed to do with a system, or just with any equation, is do some sort of operation to both sides of the equation. Right? And we take advantage of that property anytime we're solving an equation, like when we add something to both sides, or we multiply both sides by something. And so we're allowed to do that here too. And so what we want to do is pick one of the variables to eliminate and multiply one of the equations by some number to force one of the variables to eliminate when we add them together. What I mean by that is, like for example, if I want to eliminate the x's, what would I need to multiply the second equation by to make that happen? So to eliminate, say, the y's, what I can do is I can multiply the top equation by 2. Okay, and basically what I'm going to do is just sort of rewrite this equation, an equivalent form of this equation, but in a way so that when I combine the two equations, one of the variables will be eliminated. So when I multiply that top one by 2, that becomes negative 20x plus 6y equals 2. So you just multiply everything across, right? And now we don't really need this top equation anymore. This is going to be our system here. Do y'all see why I did that? Like, there's sort of a purpose behind multiplying that equation by 2. Yes, ma'am? So now that the coefficients are opposites here, when I add them together, I'll sort of get rid of the y's. So adding these together gives me negative 25x. The y's are eliminated. Negative 6 plus 6 is just 0. That's what you want to happen. So that was the whole reason why we multiplied the top equation by 2. We get negative 25x equals 23 plus 2 is 25. I'll divide both sides by negative 25 and get x equals negative 1. So now I've got the x, and now I need to get the y. From here, you sort of solve it the same way as we did before, the same way we solve by substitution. You're going to take that number and plug it back into one of the equations. And again, it doesn't really matter which one. You just kind of pick one. Would y'all rather plug it into this one or this one? First one or the second one? It doesn't really matter. You just got to pick one.
The second one.
Second one? All right. So I'm going to plug it in right there. So that'll give me negative 20 times negative 1 plus 6y equals 2. So negative 20 times negative 1 is positive 20. Then I want to subtract 20 from both sides. And you go through this normal linear solving process. It's the same steps we've been doing all year. We divide by 6, and I get y equals negative 3. So now I've got my x and my y, so I'm ready to write my final answer, my solution. I've located the coordinate where these two lines are crossing, and it's at negative 1, negative 3. All right, so let's try the next one. Now, at first glance, it looks like the x's are going to cancel out. But if I add these together, I actually get 16x, right? So what number should I multiply, let's say, the top equation by to make it so that the x's will cancel out? Yeah, negative 1. So I'm going to just sort of rewrite this top equation after multiplying it by negative 1. Y'all see why we're multiplying it by negative 1? Or not really. So when I multiply this by negative 1, that gives me negative 8x plus 5y equals negative 11. All right, so now this is set up. Right, into a convenient way where if I add these two together, the x's will cancel out here. So 8x plus negative 8x is 0. 6y plus 5y is 11y. Negative 11 minus 10. Oh, this is not going to work out very nicely, is it? Oof. Yuck. How can we make this work out a little nicer? All right, I'm gonna make an on-the-fly change here. Is that okay with y'all? Mm-hmm. Let's change this original 11 to a 12. So why would I want to do that? Yeah, I want to make this negative 22 so this works out a little nicer. All right, so when I divide both sides by 11, instead of getting that ugly fraction, I get y equals negative 2. Now what do I need to do? Plug it back in, right? Plug it into one of the equations. Doesn't really matter. I'm gonna throw it into this equation. But you could plug it into the other one if you want. Doesn't make a huge difference. So I've got 8x plus 6 times negative 2 equals negative 10. So 6 times negative 2 is negative 12. So 8x minus 12 equals negative 10. And I add 12 on both sides to get 8x equals 2. Is that right? Still going to end up with a fraction here, but that's okay. Divide by 8, and I get x equals 1/4. Looks like we couldn't avoid the fractions after all. So my solution is 1/4 comma negative 2. So again, the big idea here is to solve the system using this method, this elimination method. You want to first identify like which variable you can cancel out by adding the two equations together. If you can't, then you multiply one of the equations by something to make it so that you can. Then you add the two equations, solve for your first variable, and then just use the old substitution method to get the second one. Now there are some weird things that can happen here. So these are the special cases. For example, we saw like when we have a system of equations, there are some cases where you get no solution, right? Because you have two parallel lines that just never intersect. We also have a situation where the two equations are essentially equivalent and you get infinitely many solutions where the two lines are just right on top of each other. And so you can sort of identify those two cases when you're using elimination. And that's what I'm going to show you here is like how to know when that happens. All right, so let's take a look at this first one. It doesn't look like either one of the variables are going to get eliminated right off the bat. But what could I multiply this top equation by to make that happen? So yeah, if I multiply this by 2, I'll get them to be the same, but really what I want is for them to be opposite, so they cancel each other out. So instead of multiplying by 2, what might be a better number? Yeah, negative 2. If I multiply that top equation by negative 2, then I get 4x minus 2y equals negative 6. And you could probably see what's going to happen here. Right? If I add these two equations together, so here's my new system. I don't really need this equation anymore. Everything cancels out, right? I get 0, 0, 0. In other words, I get 0 equals 0. If this happens, if all the variables cancel out and you get a true statement, right? 0 does in fact equal 0, then that is going to be a case where the two lines are equivalent. Right? If you were to graph these, they'd be right on top of each other. So in this case, there would be infinitely many solutions. Right? And that's because you would essentially have what we call coincident lines. They're just the same line. Like if you graph them, they're just right on top of each other. Now let's try the next one. Again, nothing really cancels out here. What would we want to multiply to get this system set up a little better? How could I get this system, the second one here, to be set up so that we can use elimination? Times 2 on the second one, right? Although that can't really cancel anything out, what we really want to do is multiply it by, just like the last one, actually negative 2, yeah, to make that work out. So I'm going to write that equation above just so the equations are right next to each other. 4x minus 2y equals 10. I don't really need that one anymore. So when I go to add these together, the x's cancel out, so do the y's, but the constants don't. Right? We've got 10 plus 1 is 11. So I end up with this statement, 0 equals 11. So obviously not true. Yeah, this would be false. So in the case of a false statement, if all the variables cancel out, but the constants don't, this is a case where the two lines are actually parallel. Right? Their slopes are the same. They never intersect. And so in this case, you say that there's no solution. So these are the two special cases. Basically, if all your variables cancel out, one of two things is going to happen. Either you get a true statement, like 0 equals 0, or a false statement, like 0 equals 11. If it's true, then that means you have coincident lines. They're right on top of each other, so you have infinitely many solutions. And if it's false, that means the two lines are parallel and there's no intersection point. All right. So let's just finish this up with a couple of word problems. I think these are the hardest things because not only do you have to worry about the solving part of it, but you also have to set them up. So with these word problems, we're going to set them up, but then I want you to be thinking about like what would be the best method to solve it. Would elimination be the best way to go about it, or would substitution? And it kind of depends on how the equations actually get set up. So this says you purchase a drink and a sandwich for $4.50. Your friend purchased a drink and I guess they're really hungry, 5 sandwiches for $16.50. Write a system of equations to represent the situation and determine how much each item costs. So first let's define our variables. We'll say D is the number of drinks and S is the number of sandwiches. Okay. So for you say you get 1 drink, 1 sandwich for $4.50. So 1 drink plus 1 sandwich is $4.50. Then it says your friend purchases 1 drink and 5 sandwiches for $16.50. Now notice that when I set these up, they're both in standard form, just sort of naturally because of how the problem is worded. So when your equations are in standard form, typically you're going to want to go with elimination. Okay, now these won't, there's not a variable that will get eliminated right away here. So I'm going to have to multiply one of the equations by something. What am I going to want to multiply, say, the first equation by? To make it so that I can cancel out one of the variables. So yeah, I've got kind of 2 options, right? I can multiply this by -5 to get rid of the s's, or I could multiply it by -1 to get rid of the d's. Either way is fine, quite honestly. So I'm going to go with -1. Just to keep my numbers a little smaller. So that changes this equation to -d minus s equals -450. And I don't need this equation anymore. Now I might use that equation later on to plug it in, but you really don't need it for the most part. Now when I go to combine these equations to do the elimination process, d minus d is 0, that cancels out, that's what you want to happen. 5s minus s is 4s, and 1650 minus 450 is 12. So how much does a sandwich cost? $4.50?
Drink and a sandwich.
$3. Yep. So now I got the sandwich. I'm going to go back and plug this into I'm actually going to use that original equation that I crossed out, just because it's got the least amount of stuff going on in the equation. So D plus 3 is 450. Subtract 3 from both sides. And I get D is 150. So now I have the solution to the system. I've got the answer to the question, which is that sandwiches cost $3 and drinks cost $1.50. Okay, so this page has $7.75 to buy 12 sheets of felt and cardstock for her scrapbook. The felt costs 50 cents per sheet. The cardstock costs 75 cents per sheet. How many sheets of each can Paige buy? So let's first define our variables. So let's see, we've got felt and cardstock, so I'll do F and C. So F can be the number of felts felt sheets, and cardstock, so C could be the number of cardstock sheets. So she's got a total of 12. That means that F plus C has got to be 12. And if she spent $7.75, then we have to multiply each one of these, how many she bought, by the cost. So our two equations here, one is talking about how many we have, and one's talking about what the cost is. So we've got, let's see, felt is 50 cents, so 50 cents for felt plus 75 cents for cardstock equals $7.75. So the numbers here probably are not going to be too friendly. That's okay. We've got two options here, though. We could multiply this equation by something like negative 50 cents or negative 75 cents. Or we could multiply this by something that sort of get rid of the fractions or the decimals. So instead of multiplying this top equation by, say, negative 50 cents to get rid of the F, what could I multiply the bottom equation by to force this 50 cents to 1, or negative 1, I guess? What would I want to multiply this second equation by so I could eliminate the F's? Yeah, negative 2. Good. So I'm going to multiply that second equation by negative 2 to give me negative 1F, so negative F minus 75 cents times 2 is $1.50, so minus 1.5C equals negative 15.5, I think. I don't need this equation anymore. So now I can get the F's to eliminate. So F plus negative F is 0. C minus 1.5C is negative 0.5C equals 12 minus 15.5 would be negative 3.5. You'd probably want to use a calculator for this one. Dividing by negative 0.5. What would that give me? How many cardstock sheets did she buy? Think of it like this. You might not even need a calculator, right? How many times does 5 go into 35? 7, yeah. Now to figure out how much cardstock she bought, we're going to plug that into the most convenient equation, which is probably this one. F plus 7 equals 12. So how many sheets of felt did she buy? Yeah, 5. So we have 7 sheets of cardstock and 5 sheets of felt.